Okay, in today's lecture, we are going to pick up from our last week's discussion of our last class discussion of sampling of multidimensional signals, and we were pretty abstract in our discussion last class. This class, we are going to focus exclusively on two-dimensional signals, which are the best example of that is images, although you can also sample two-dimensional signals. For example, if you are measuring temperature in an area, which is two-dimensional. So it's not really restricted to images, but most of the time you will be using it for images. So we are going to do sampling theory for two-dimensional signals or images. And last time where we finished was the Shannon-Nyquist sampling theorem. So sampling theorem for 2D signals. I'm just going to repeat that for the sake of continuity. So the assumption is that you have a two-dimensional signal, f of x, y, and it is band limited to omega n1, omega n2 radians. If you are talking about spatial signals, we will just say radians per meter. Then we can sample this continuous signal by taking its pointwise samples at regular spaced intervals. So it can be uniquely recovered from its uniform pointwise samples given by f of nm equal to f of n over x, m over y, where n, m, they are from 0, plus, minus 1, and so forth, as long as the following Nyquist criterion is satisfied, which is that your sampling frequency in the x direction, which is omega s1, which we write by 2 pi over x, that is greater than twice the bandwidth in the x direction, and omega s2, which is given by 2 pi over y, is greater than or equal to twice the maximum frequency in the y direction. Okay? It's a simple extension of the one-dimensional signal that we saw many lectures ago, where the idea is you have just one frequency, so your sampling must be at least, your sampling frequency must be twice your highest frequency. Now we have two frequencies. In the last class, we went over what do these two frequencies mean in terms of, for example, sinusoids. So the idea is that now you want sampling in x and y direction to be such that your sampling frequency is twice the highest frequency in x direction and y direction. So thinking about the example in the case of just images, effectively what you're talking about is if you have, let's say if you have an image or a scene like this, and you believe that what you're looking at, this scene, this object, if you take its Fourier transform, then it's band limited to omega n1, omega n2. So the idea is that the Fourier transform of that, the 2D Fourier transform, if you look at it, that's contained within some rectangle where this part of the rectangle is omega n1 and this part of the rectangle is omega n2. Okay? So it's your Fourier transform, if this image is contained within this omega n1, omega n2 rectangular region, then what the sampling theory is saying is that you can take uniform samples of this thing. Okay? So you can only measure at these points, these red points that I am drawing. where the distance between 2 points is 1 over x in the x direction and 1 over y in the y direction. And these distances have to be related, which define your frequencies. So this distance defines your frequency in x direction, or sampling frequency 2 pi over x. And this defines your sampling frequency of 2 pi over y. And so this must be bigger than twice omega n1 and omega n2. If you do that, then these few points are enough to reconstruct your original two-dimensional signal, scene, object, whatever you want to call it. And the reconstruction formula is very similar to what we saw in the 1D case. So the reconstruction formula is simply then saying if you satisfy this, then you can recover f, I'm going to call that f hat, by simply doing sink interpolation in 2D. So it's now you have a two-dimensional sink. Okay? So you take your samples n, m, and you take a two-dimensional sink x minus nx over x. So just similar to in the 1D case, it was sink of t minus nt over t. Now you have sink of x minus nx over x, which is sink in one direction, and sink of y minus ny over y. You multiply each of these samples with these sinks, which are just shifted in space by x and y amount. And you add all of them up, and you are guaranteed to get back your f hat fxy, which is equal to fxy if your signal was indeed band limited. Okay? And the usual notation that we will use, we will follow the same notation that we saw earlier in the discrete case that you have in the one-dimensional case, that you are going from continuous domain to discrete domain by sampling in space at a rate of 1 over x and 1 over y, so you get f of n m, which is simply equal to f of n over x m over y. Okay? So very similar to the 1D case, a simple extension of all the same concepts. And as we will go along, we'll see that even the concepts of how are the Fourier transform of the continuous signal related to the Fourier transform of the discrete signal, how do you do interpolation, decimation, all those concepts of aliasing just trivially translate into the 2D case. Okay? So all of these are typos. This should be n times x, and this should be, so you take every x steps and every y steps, so nx and y. And similarly, the distance between two samples is therefore just x. In x direction, the distance between two samples in the y direction is simply y. And here in this sink, instead of n, I should have m. And similarly, this needs to be corrected. This is nx and my. Nx and my. So the way to think of it is, previously we had time samples, and this x now takes the place of capital T, right? So this x takes the place in the x direction. You are taking samples every x distance. In the y direction, you are taking samples every y distance. And of course, this x and y are very small numbers if you want to be able to reconstruct your original image or signal. Okay. Now, just like we did in the case of the 1D signal, instead of just writing that we have this continuous to discrete block, which is fine as far as representing the abstract notion goes, we want to actually write it in 2 steps so that we can do the analysis as far as understanding what happens when we do the sampling operation. So the kind of breakdown of this thing mathematically is very similar again to the case we did in 1D, which is that instead of writing this block, we will say that you first get your signal and then you multiply it with a direct comb in 2 dimensions. Okay? So if you recall, in 1D we used to have this direct train, right? Now we'll have a 2-dimensional version of the same thing, which simply puts a direct delta, an impulse, at every x units in x direction and every y units in y direction. So effectively you have, if you look at your 2D plane, you have these combs going here, here, right? And the distance, the distance in this direction is x, the distance in the y direction is y. Okay, and they just keep on getting replicated upside down. So you have now this 3-dimensional picture where they are effectively, these impulses are sticking out of the plane. And then we get this fsxy, just like the 1-dimensional case, which is simply then given by, because of the shifting property, since these are just impulses, because of the shifting property, you can write down that that will be f of nm delta of x minus nx delta of y minus my. Okay? And then you take this fsxy and you simply convert it into a 2-dimensional sequence, convert to 2D sequence by effectively reading off these coefficients that are associated with fsxy. So you get f of nm. Okay? So very similar thing that we did in the 1-dimensional case. We multiply our signal with an impulse train, and then we just read off the coefficients of that impulse train, and those are our sequence values. Again, in reality, you won't be doing that. The only reason we are doing it is because we want to understand what is the impact of this sampling operation. Now, we'll go through the same steps that we went through when we did the 1-dimensional sampling case. We want to understand what is the Fourier transform of this fsxy in relation to my original signal. So let's say my f of xy has this Fourier transform, and now we are talking about 2D Fourier transform. I'm going to write that as f j omega 1 omega 2. Okay. Now we won't do it here, but just like you did for the 1-dimensional case, you can show using a 2D Fourier series. So in the 1-dimensional case, we use the 1D Fourier series to show that the Fourier transform of an impulse train is nothing but an impulse train. Similarly, the Fourier transform of a 2D comb is nothing but a 2D comb. In the appropriate fashion, if you remember the formula, for 1D it used to be 2 pi over t. In the 2D case, you will have 2 pi square over x and y. Okay? Instead of one summation, you have 2 summations, m, n, and you have a comb which is now periodic with a period of omega s1 and omega s2. Okay? So in 1D case, the periodicity was given by 2 pi over t. Now the periodicity is given by, in the x direction, it is given by 2 pi over x and delta of omega 2 minus 2 pi m y. Okay. So the Fourier transform of a comb, which is shown here above, will look exactly like that. The only thing will be that the distance between the two impulses in the x direction now will be 2 pi over x. The distance in the y direction will be 2 pi over y. So what we want to understand is the Fourier transform of fsy, which is simply the multiplication of xy and s of xy. And just like the 1D case, once again, multiplication in time is going to give you convolution, but now the convolution will be the 2D convolution. Okay? And there will also be a factor of 1 over 2 pi square because we are dealing with radians. So f of j omega 1, omega 2, convolved with, and when I write this, this is implicitly convolution in 2 dimensions, times s of j omega 1, omega 2, which is convolution of this function sxy. Okay. Now, I just plug that in, so let's call this fs j omega 1, omega 2. And if I apply the convolution formula, I get 1 over xy summation of m, summation of n. Because convolution is linear, I can just take this inside f of j omega 1, omega 2, convolved with delta of omega 1 minus 2 pi over n over x times delta of omega 2. So delta of omega 2 minus 2 pi m over y. Okay. Now, effectively what this is saying is you have a two-dimensional function. So this is a 2D function, okay, which is getting multiplied by an impulse in 2 dimensions. Okay, so this is an impulse which is located at location omega 1 equal to 2 pi n over x and omega 2 equal to 2 pi m over y. So this is an impulse which is just located at some location, and the location of this thing is 2 pi n over x, 2 pi m over y. Okay. And if you go through the convolution formula, the 2D convolution formula that we saw earlier, so the effect of convolving something with an impulse in 2D is exactly the same as the effect of convolving a function in 1D. What happens in the case of a one-dimensional convolution with an impulse in 1D? The whole function gets shifted to the location of that impulse. Okay? The exact principle happens here. If you convolve, so let's say you are given some g of xy, and you convolve that with delta of x minus x naught, delta of y minus y naught, the output that you will get will be g of x minus x naught, y minus y naught. Okay? The whole function will get centered, instead of at 0, it will get centered at x naught, y naught. So by that token, this convolution of the Fourier transform of my function f of j omega 1 omega 2, when I'm convolving that with an impulse which is located at 2 pi n over x, 2 pi m over y, this whole Fourier transform gets shifted to the location of 2 pi n over x and 2 pi m over y. Okay? So effectively, by that token, I see that f of j omega 1, omega 2, if I convolve that with delta of omega 1 minus 2 pi over n, 2 pi n over x, and delta of omega 2 minus 2 pi m over y, that will simply be equal to that my whole function gets moved to 2 pi n over x and 2 pi m over y. So if I write down that whole expression, my fs of j omega 1 omega 2, that is then simply equal to 1 over x y summation of m summation of n fs j of omega 1 minus 2 pi n over x and omega 2 minus 2 pi m over y. So that is what happens when you multiply your signal with this periodic comb in the 2 dimensions. You get multiple copies of your signal. So this shouldn't be fs. You get multiple copies of the Fourier transform of your original signal shifted by amount 2 pi over x and 2 pi over y in x and y direction, and there is this scaling 1 over xy. Very similar to the 1D case where you had 1 over t here, and your function was just getting shifted by 2 pi over t, multiples of that. Okay. So what is effectively happening if we first understand, for example, what happens to the case when I shift. So let's say that my Fourier transform looked like this. Let's use a version of that triangular thing in 1D. So let's say my Fourier transform sort of looks like this in 2D. Okay, it's supposed to be a pyramid. It doesn't look like that because I am not that great at drawing. But this thing gets shifted to 2 pi n over x1 and 2 pi m n over x and 2 pi m over y. So right now it's located at 0, 0. Okay, and this whole thing gets moved to, let's say this is where 2 pi n over x and 2 pi m over y is. So this whole thing gets moved here. Okay. And now what is happening is that you have multiple copies of this thing at every multiple of 2 pi over x and 2 pi over y. So now I'm not going to draw the 3D picture because, first of all, it doesn't look good, and secondly, it's very hard to keep on drawing these multiple times. So let's now just assume that your function was supported on this. I'm just now drawing the support of my Fourier transform, okay, where this is omega n1 and this point is omega n2. And this is my f of j omega 1, omega 2. Okay. So what this picture shows is this is where the Fourier transform is non-zero. What is on top of that, I'm not plotting that. Okay. Now when we multiply it with the comb, so when we multiply it with s of xy, the Fourier transform basically gets shifted at multiples of these points. So what I have is this 2D plane. So this is 0, 0. This is 2 pi over x. This is 4 pi over x. Similarly, this is minus 2 pi over x. this is minus 4 pi over x, and this is 2 pi over y, this is minus 2 pi over y, and then you have all those points repeated. Right? So you have effectively a lattice in the 2D, and your Fourier transform gets moved to these lattice points. You get one copy here, you get one copy here, you get one copy here. Similarly, you get one copy here, one copy here, 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 at this point, and this will sort of keep on repeating like that. Okay. Now, if you notice, I was very careful about making sure that this edge does not overlap with that edge. Right? But that can only happen under some assumption. So if this point, remember, this is 2 pi over x and 2 pi over y. Right? So this endpoint is in the x direction. I haven't changed in the y direction, so this endpoint is 2 pi over x minus omega n1, right? And 2 pi over y. And if I come here, if I look from this point, this endpoint also corresponds to omega n1, right, and 2 pi over y. And similarly, you can do that for all the endpoints. Right? So the reason that, or the only way that we won't have overlap of these pyramids is only you can pick up any two copies. For example, it won't have overlap in this x direction if this omega n1 is bigger. So if omega n1 is smaller than or equal to 2 pi over x minus omega n1, which implies that only if your 2 pi over x is greater than or equal to 2 omega n1, which is the criterion that we had listed for sampling of 2D band limited signals for the x direction criterion. Okay? You can do the similar thing if you keep your counting right. You will arrive that if you don't want any overlap in the y direction, then you better have that 2 pi over y is greater than or equal to 2 omega n2. Okay? So if you don't have these overlaps, then you can see that the Fourier transform of your original 2D signal is preserved in this repeated copies version. And if someone were to ask you recover that Fourier transform, you could simply just look at this region and throw out everything else except this region, which corresponds to simply a block in 2D, where this region has width of 2 omega n1, because it goes from minus omega n1 to omega n1, and this region has width of 2 omega n2. Okay? So I could simply remove this by doing what's known as low-pass filtering in the two-dimensional plane, right? Two-dimensional low-pass filtering. I can simply multiply the Fourier transform with this box kind of a function, and everything will become 0 except the region in the middle, centered at 0, 0. It's just an extension of the one-dimensional low-pass filtering. Now you are saying you want to throw all frequencies which are bigger than omega n1 in the x direction and omega n2 in the y direction. Okay. The condition for that is that you have no overlap. In that case, you can simply low-pass filter that and you get back the Fourier transform of your original signal, which means you get back your original signal. And if overlap does happen, and I'll just draw one version of that. So let's say here was one copy, here was other, and the distance was not if you didn't sample at a high enough rate, then what you get is that you have overlap happening in this region, overlap, which is again just the same principle that we saw in one dimension, as if you are folding your higher frequencies into lower frequencies. Okay. Similarly, if you had overlap in the y direction, if you didn't sample at a high enough rate, you could have overlap here. Okay. And now when you filter, you will lose some information. This principle, again, just like the case of one dimension, this overlap principle is called aliasing in 2D also, which means that you have frequencies which appear as lower frequencies. Okay. And when will that happen? When you don't satisfy the Nyquist criterion. So you will have aliasing if 2 pi over x is less than 2 omega n1, or 2 pi over y is less than 2 omega n2. Okay? If either one of these conditions is not satisfied, you would have aliasing. So it's exactly the same principle that we saw in the case of one-dimensional case. In particular, given a sampling system for two-dimensional signals, if your sampling rate, so the highest frequency in x direction that can be handled is without aliasing. So in the 1D case, that is pi over t. In the 2D case, in the x direction, it's pi over x. And in y direction, it is pi over y. Okay? Otherwise, you would have aliasing. If you are talking about images, then we talk about aliasing in spatial frequencies, in space frequencies. Okay. So what's the significance of this from the perspective of if we now specialize ourselves to the case of, let's say, images and digital cameras? Okay. Well, it's very easy to understand from the sampling theorem. While a digital camera has many approximations, if we throw away those approximations and let's assume that what a digital camera really does is it looks at the scene and it just takes point-wise samples. Okay? So if the images that a digital camera is taking, has not too many high frequencies, compared to the resolution of the camera. What does that mean? Our camera, if you just think of it that it is just taking point-wise samples, then you can say, well, my camera has these pixels. Okay. In reality, these pixels are rectangular, but I'm just going to assume that they are just point samples. So my camera is just taking point samples. If my camera has enough resolution, enough pixels, enough point samples, so let's say it's 10 megapixels versus 1 megapixels, right? Then because of the fact that it's 10 megapixel within some range, its pixels has some distance between them. Well, based upon that, it can handle certain high frequencies, but not very high frequencies, okay? So if the images that digital camera is taking doesn't have too many high frequencies, then you get no aliasing, and the picture looks pretty good, and you're happy. On the other hand, it could be that either the distance between the sensors is high, the number of sensors that you have, the number of pixel count of your camera is low, or that the image you are taking has really high frequencies. So if the image has high frequencies, then the image taken by the camera will have aliasing. Now I want to make sure you understand that in reality, when we talk about really optical photography, there are way too many details than what we are covering, okay? It's not just the pixel count that matters. There are a number of other things, but we are right now just abstracting all of those things away, and we are just talking about basic principles, okay? In general, just because a camera has 10 megapixels versus someone else having 7 megapixels doesn't make that camera better. But this is not a class about acquisition of images. Now, I'm not sure if you have seen these pictures or not, but let's try to examine those. So here is an example. We have Miley Cyrus. She's no longer Hannah Montana. And we can safely say that the frequencies in this image, the frequencies of the scene, were not that high enough compared to the resolution count or the intrinsic sampling rate of the camera with which this picture was taken, and we don't see any visible aliasing effects going on. So this is sort of a good picture, good image, no aliasing. And why we can say that no high frequencies are present? Remember, frequencies are all about a rate of change of your signal, right? So the background of this image is pretty plain. Things are not changing very fast. Her face is sort of uniform. She's wearing a plain kind of a shirt or blouse, right? And because of that, the image, if you really think of it, it doesn't have high frequencies because of the fact that things are not very sharp edges. Okay? So in images, edges, one way of thinking of whether a scene has high frequencies or not is just thinking of the edges. And because what is an edge? That's a discontinuity. In her case, it's not that bad, and so we don't see very visible aliasing. Okay? On the other hand, if you go to this image, which could have, for multiple reasons, it could have that. This is an image of a building which is brick walls. Right? And bricks effectively have these edges time after time after time. And what you notice is, because of that you have these strange kind of patterns appearing. Okay? You have these sort of circular patterns appearing which are called Moire patterns. These are telltale signs of aliasing. Okay, and this is not just the case. If you see pictures, go to Google Images, search for pictures where someone is wearing really stripy dress. Okay, there are too many stripes in the image, and you will see the same distinct pattern appearing again. That's a telltale sign of aliasing, because this image, the object that you're trying to image, has too high frequencies, but the sampling that you are doing is at a lower rate. You can't manage the high frequencies of that image. So because of that, you start seeing these Moire patterns. So there are higher frequencies, they folded into lower frequencies, and those lower frequencies are going to have now a different pattern than the pattern that you had in your image. Okay? That's why if you have really detailed texture, taking images of a texture is really hard with crappy cameras. They don't capture it well. These patterns are telltale signs that you have aliasing going on. So we have now discussed the concept of aliasing in two-dimensional signals, and we have also talked about how does that two-dimensional aliasing manifest itself, at least in images. It manifests as these Moire patterns. Now, the question is, how do we then avoid this aliasing? And how to avoid aliasing? The answer is the similar as in 1D case. The only way to do that is do anti-aliasing filter. Okay? So before you sample your signal, you must pass it through a filter, a two-dimensional filter, whose Fourier transform is a box function. Okay? This is the Fourier transform that I am drawing, h of, let's call it anti-aliasing j omega 1 omega 2, which is simply defined as that it is 1 as long as omega 1 is less than or equal to pi by x, and omega 2 is less than or equal to pi by y, and 0 otherwise. So a filter which kills all frequencies higher than pi by x and pi by y. Just like the 1D case, extension of that to 2D, you do that, and you get your FAAXY, and now if you sample it, you will have very little trouble. Now in the case of images, this is called optical low-pass filtering, and that's where things start to diverge. Because in the one-dimensional case, you can build electronics to do low-pass filtering. In the two-dimensional case, how do you implement that becomes an issue, and the way you do it is through optical systems. And while optical low-pass filters do exist, they exist only in very high-end cameras because it's an expensive thing. Okay? Most low-end cameras won't have this optical low-pass filter in them. And what the effect of that, if you go and search for optical low-pass filters, you will get many chips. What an optical low-pass filter looks like is that just before the sensor, you will have this device which is sort of doing low-pass filtering. And the effect of that, you can compare, for example, if you have this kind of an image, on the left is the scene imaged without having the optical low-pass filter. On the right is the same thing with the optical low-pass filter, and you can see that you have these patterns appearing, false patterns, these Moire patterns, because of aliasing in this on the picture on your left-hand side, whereas the right-hand side one, which has been filtered before taking samples, has very few of those. Okay. Now building that in the hardware in a nice fashion, that's a different topic that we won't go into. But optical low-pass filters do exist. In imaging, actually, we also have this sort of blessing in disguise, if you want to talk about it, which is that most realistic imaging also has some sort of low-pass filtering actually happening in it. What happens is in digital cameras, and now we are talking about very specific application of two-dimensional sampling. In digital cameras, in reality, you take samples through these sensors, which are called these Ccd arrays, which are nothing but basically these sort of your whole plane where light shines is divided into these rectangular regions, and each pixel actually corresponds to sort of an average, an integration of all the intensity that falls on one cell of this array. So this is just cell which gives rise to the pixel. Okay, and this is the Ccd array, which does the sensing. And if you actually do sort of analysis of that, because of the fact that you are doing sort of this integration operation on 2D, this thing at some level also acts like somewhat of a low-pass filter. It's not exactly a low-pass filter. Okay, it's very similar to the block sampling or the case of it's as if you are assuming your signal to lie in a piecewise constant world. Okay, it's very similar to the piecewise constant assignment that you did, where you're taking your signal and you're replacing them with one value over some region. Okay? So because of that, you have inherently some low-pass filtering going on, but that is still not that strong of a low-pass filtering. Now, there are many other details associated with exact image capturing using Ccd arrays and what does it mean in terms of the mathematics and low-pass filtering and all that. We are not going to go into those details. That goes into the whole different topic of optics, and if you are interested, you can from here move on to that field or literature on that. Okay, but we are sort of going to end the discussion up to this point, which is that you have aliasing of 2D signals in images. This aliasing manifests itself as more patterns, and if you are interested, you can avoid that by doing low-pass filtering, although that may not always be feasible in the case of two-dimensional signals. Okay. Now, we won't spend too much time on the other cases, but it is important for you to at least realize that in a very similar fashion to what we have been doing before, extensions of the Shannon-Nyquist sampling theorem to more than 2 dimensions is also trivial. To n dimensions. Of course, that requires us defining the concept of Fourier transform in n dimensions. But that is, again, very similar if you say that your x, or let's say f of x1, x2, up to xn. So it's a function of n variables. If it belongs to L2 Rn, which means that if you take its n-fold integration of f of x1, x2, up to xn, and you take the absolute square and you integrate it up to dx1 to dxn, the answer is less than infinity. So it's a finite energy signal. If that is the case, then you can define Fourier transform, n-dimensional Fourier transform of this thing, which is f of j omega 1, omega 2, up to omega n, which is simply given by trivial extension n-dimensional integral of your function xn e to the minus j omega 1 x1 plus omega n xn, and then you simply integrate from dx1 to dxn. Okay? Which is effectively saying that you want to represent your n-dimensional signal now as a linear superposition of n-dimensional sinusoids. It's complete generalization of one-dimensional sinusoid, two-dimensional sinusoid, and so forth. Okay? And the definition of a band-limited signal in n dimensions is simply that f of x1 up to xn is band-limited to omega n1 up to omega n little n if basically the signal has no higher frequencies in one direction, in x1 direction no higher frequency than omega n1, in x2 direction no higher frequency than omega n2, and so forth. So if the Fourier transform becomes 0 for all omega 1 absolute value greater than or equal to omega n1, omega 2 absolute value greater than or equal to omega n2, and omega nn greater than or equal to omega n little n, omega little n bigger than or equal to omega n cap little n. Okay? And if you have a band-limited signal, then you can actually state the same theorem, and as you would expect, it will have exactly the same form. You can take samples of your signal at regular intervals, and you can reconstruct them as long as the sampling frequency in each direction is twice the maximum frequency in that direction. So the theorem says, sampling theorem says that you sample f of x1, x2 up to xn at as follows. You basically f of m1, m2 up to mn is defined as f of m1 x1, m2 x2, mn xn. Okay, so in the first dimension you sample it every x1 units. In the second dimension you sample it every x2 units, and so forth. Okay. And if you do this, then as long as the sampling frequency in each direction, so omega s1, which is defined by 2 pi over x1, if this is greater than or equal to twice the highest frequency in that direction, omega s2, which is defined by 2 pi over x2, that is greater than or equal to twice the highest frequency in the second direction, and keep on going, omega Sn, which is defined by 2 pi over xn, that is greater than or equal to 2 omega n little n. If that is satisfied, then f of x1, x2, xn can be perfectly recovered from these samples using an n-dimensional sinc interpolation. N-dimensional sinc interpolation. And that n-dimensional sinc interpolation, again, it's a trivial extension f hat of x1, x2 up to xn is simply given by you just sum over all the indices m1 up to mn. You take your samples fm1 up to fmn, and then you multiply them with this n-fold sinc. you have sinc of x1 minus n1 x1 over x1, and n such sinks. Together they give you an n-dimensional sink. Xn minus, sorry, m1 mn xn over xn. Okay. So that's a generalization. Based upon that, you can talk about, okay, how should you be doing sampling, for example, for taking video. So typical video is done, for example, 30 frames per second, but that requires, so the third dimension, if you're talking about video, the third dimension now is the time dimension. Okay? So if things are not moving very fast, then you can do 30 frames per second. What does that mean? That you are taking a sample every 1/30 seconds. Okay? But if things are changing very fast, for example, these sports videos, right, where you have very fast action happening, if you want to capture that well, you must have a camera that takes more than 30 frames per second. If you want to image a rocket which is going very fast, you better have a camera which is taking way many samples so that you don't have this blurring effect. You don't have this aliasing in the time dimension. Right? So these notions can be generalized to multiple dimensions, and we don't have to reproduce the Shannon-Nyquist sampling theorem for every case. If you understand one dimension, if you understand two dimensions, extensions to that in n dimensions is trivial. N can be 3, 4, 5, 6, depending upon the kind of application you are doing. And the key is that the sampling rate in each direction must be proportional to how fast you expect things to vary in that direction. If you are imaging a 2D plane and the image is mostly about, let's say, a background which is white or some other color, plain, right? You actually don't need that many samples. You don't need a high resolution camera because of the fact that their changes are not happening that fast in that scene. Okay? So it's all very simple extensions of the one-dimensional case that we have studied. We won't spend any other time about these n-dimensional sampling, but you can very trivially redo all the steps that we have done before. So the next goal for us, we just took a detour, but I wanted to just give you a sense of what the sampling theorem would look like in general. We want to step back to the 2D case again. Okay? So in the 2D case, we have discussed the sampling theorem, and we have also figured out what is the relationship between the frequencies of this direct comb sampled. When I multiply my signal with that direct comb, what is the Fourier transform of that in relation to my original signal? I take my Fourier transform, I just shift it within the plane, and I have a scaling of 1 over x and 1 over y. Okay? But in reality, what you really want to do is, let's say you get an image or some other two-dimensional signal inside your computer. So you are given f of x, y. You have sampled that using a continuous discrete with x and y sampling rates. And you get f of n m. And this is what you have gotten inside a computer. And you now really want to do analysis about frequencies of this thing. Well, you better be able to tell how are these frequencies of this discrete two-dimensional signal or sequence related to this continuous signal, this continuous two-dimensional signal, which is what we already know in the case of one dimensions, right? But we want to rederive that expression for the two-dimensional case, even though we think it should look very similar to the one-dimensional case. Okay? But to do that, we first need to talk about what do frequencies mean in 2 dimensions. And by now, you guys should be becoming an expert at understanding that all the things that we have done in 1D have more or less, with a few caveats, easy extensions to 2 and higher dimensions. So if we are talking about a discrete sequence, f of nm, then just like the 1D case, we should be able to say, well, a 1D case, we said, has a discrete time Fourier transform, which tells us what kind of discrete frequencies exist in that signal. A 2D sequence should also have a similar thing, right? And indeed, we can actually talk about frequencies in F and M by talking about a 2D discrete Fourier transform. About 2D discrete, and just to avoid confusion with something that we will learn later, which is the discrete Fourier transform, I'll just specify discrete spatial Fourier transform. Okay. So if you remember, in the 1D case, we have x of e to the j omega, which is the Fourier transform of xn. That is defined as simply summation over n, xn, e to the minus j omega n, which effectively means that you are saying your signal, your Fourier transform is given by this, and your xn is given by 1 over 2 pi minus pi to pi x of e to the j omega, e to the j omega n d omega, where this thing simply says that your signal is made up of a superposition of discrete sinusoids with frequency omega. Okay? A similar notion exists in 2D. So we can talk about, given f of nm, we can talk about its 2D spatial Fourier transform, which we will write as f of e to the j little omega 1 little omega 2. Okay? Again, since we have 2 indices, we should have frequencies in 2 directions. And I'm not going to again show you the same videos that pictures that I showed you for the continuous case, but it's exactly the same thing. So that is defined as, if you want to extend the analogy, now you have summation over the 2 indices, m, n, and similarly you have j omega 1 n plus omega 2 m. Okay? And if you want to talk about the inverse Fourier transform, that is simply given by 1 over 2 pi square minus pi to pi minus pi to pi. Okay? Just like the 1D case, this thing is periodic in x direction and y direction with period 2 pi. So you have 2 integrals. You have f of e to the j omega 1 omega 2 e to the j omega 1 n plus omega 2 m d omega 1 d omega 2. And if you focus on this part, what this is saying is that, again, your signal, just like we saw for the continuous 2-dimensional Fourier transform, your signal is made up of these sinusoids. This is a sinusoid, a discrete time sinusoid of frequency omega 1 in one direction and omega 2 in the other direction. So this is a sinusoid, and this Fourier transform tells you how much of that frequency is present in your signal. Okay? And your signal is just given by superposition of an infinite number of these discrete frequencies. So the same notion applies in the 2D case. And what we want to now figure out is what is the relationship between this Fourier transform of a discrete sequence if that sequence was obtained through sampling of a continuous signal f of x, y when the sampling was at a rate of x and y. Okay? So that's our goal. We want to relate it to the Fourier transform of the continuous signal. Again, the analogy is, if you remember, if we are given x of t, which had a Fourier transform of x of j omega, then we know if we do a continuous to discrete conversion with time period t, we get xn, which has a Fourier transform x of e to the j omega, and we know the relationship between the two. What is the relationship? The frequencies in this correspond to just scaled frequencies of your continuous time signal. The amplitude is scaled by 1 over t, and all of those get shifted by a period of 2 pi. Right? So if you remember your formula, that is given by simply k minus infinity to infinity x of j little omega minus 2 pi k over capital T. Right? You do scaling of your frequency axis, you then shift those things by a period of 2 pi, and you have a scaling of 1 over t of the amplitude. We know that relationship in the continuous time one-dimensional signal. Our goal is, can we derive the similar kind of expression for two-dimensional signals? Okay? And as you would expect, the relationship will be exactly the same, where this one shift will be replaced by shift in both x and y direction. So that is where we will pick off from the next lecture.